And I'm going to send a message your way that I periodically do throughout my courses, because there are always students in high school math who, and I was one of them, who can kind of just sit back and observe and do the math, no problem. But then, like me, when I was in high school, I hit the wall, I call it, near the end of grade 11, and some students hit the wall in grade 9, some hit the wall in grade 10. They're the students who were like me, that just kind of sat back and observed and understood it all. And then I realized at some point that I had to do a fair amount of work in order to be successful. And it was near the end of grade 11 where all of a sudden I realized my marks started to slide. I didn't have a really good understanding of material. And I think it's because the material gets a level of complexity sooner or later that's, for most people, it's just not possible to just kind of let it all sink in. So the message I want to send today is some of the work we're going to be doing today, you need to follow along very carefully with, and you need to do the work. The trigonometry that we're going to be dealing with at times can be quite complicated. And if you don't pay attention and follow the advice that I give you in terms of how to do the math, you could be in trouble. We're looking here at 2.1, which is angles in standard position part 2. We're going to be looking at two things. The first thing is really simple, I think. It's the second thing that can be quite messy. The first thing is, what happens to a rotation angle when we reflect a terminal arm across one of the axes? And the second thing is going to be finding trigonometric ratios of what we call special angles. By the way, primary trigonometric ratios are the sine of an angle, the cosine of an angle, and the tangent of an angle. The reason why they're called primary is there's another set of trigonometric ratios which are called reciprocal trig ratios that we learn about in Math 30. They're called secant, cosecant, and cotangent. So to begin with here, just a statement about reflecting terminal arms. It turns out that when you reflect a terminal arm across an axis, either the horizontal x-axis or the vertical y-axis, the reference angle remains the same. And we're going to learn about this through examples, so you don't need to write this down. But if I were to take a look at a terminal arm, and it doesn't matter which quadrant I'm going to put it in, which quadrant, 1, 2, 3, or 4, Christy? 2. So we're going to use a terminal arm in quadrant 2. Let's just say that that's the terminal arm. And I'm going to reflect that. Do you want me to reflect it? Do you want me to reflect it in the y-axis or in the x-axis? Let's go x-axis. So what does a reflection mean? When I look at myself in the mirror in the morning, I can see my image there. I'm smart enough to know it's not a real person. It's just an illusion. It's something that I observe. But I can make an observation that the razor I'm holding in my hand is a certain distance away from the mirror. And if I could get into the mirror and into that world, the distance from the razor in my image to the mirror would be the same. That's how reflections work. And what that means is that if the distance from the tip of that terminal arm to the x-axis is that amount, and I reflect that vertically, then what's going to happen is the new terminal arm, instead of being up there, the new terminal arm will be there. And it's pretty easy to use basic geometry to show that those two triangles that you're looking at are similar. They have the same length for the hypotenuse, and that side that I've labeled as a green squiggly line is the same length. And what that means, if they're similar, is that this angle, which is the reference angle for this rotation angle that we started off with, that angle is the same as the reference angle for the new rotation angle. There's a new rotation angle. Maybe this original rotation angle is 120 degrees. This rotation angle is sure not 120 degrees. It's more than 180, but it has the same reference angle. And had we chosen any other quadrant, and had we chosen to reflect it in the other axis, the same thing would be true. You're always going to get the same reference angle. So, sketch a rotation angle of 38 degrees. Well, that's pretty easy. 38 degrees is a little bit less than 45. So when I draw this, and when you draw it, you're going to draw a line with its vertex at the origin, pointing. And when I say pointing, that just means we need an arrowhead on the end of it, so that we have an angle of 38 degrees in a counterclockwise direction from the positive x-axis. That's the rotation angle. And it even says here, theta rotation equals 38 degrees. The question is, what's the reference angle? And it's not a trick question. The reference angle is also 38 degrees, isn't it? We learned that yesterday. So the reference angle is also 38 degrees. And just a reminder, and in case you weren't here yesterday, I'll make the point. When I talk about a rotation angle, let me draw in, or let me write in the reference angle as well. When I talk about the rotation angle, there's a direction associated with it. The rotation angle is indicated in what I've got in red, and there's an arrowhead on the end of the arc. It shows the direction of the angle. Whereas the reference angle, which is in green, has no direction associated with it. It's just an amount. So now the question is, and there's something about B here that I have to try to get as many grade 11 students to understand something so you don't get burned in grade 12. And in grade 12, there's this idea we're going to talk about where I tell the students, look, you cannot make this mistake. And I go over it and over it and over it, and students still make the mistake. And that's that they don't know what this is. We're told we're going to reflect the initial arm, and if you like, you can redraw the initial arm here. I think it's not a bad idea. This is the initial arm. Okay, I'm gonna write something here. I'm gonna say this is the original rotation angle termination. Okay, we're gonna reflect it in the line y equals 0. And the question is, what is the line y equals 0? Yeah, it's the x-axis. And that can be a little tricky because you see the letter y and you say, well, the y-axis. But think about this. Forget about what we're doing here. This would have a y-coordinate perhaps of +3. This would have a y-coordinate of -3. Any place here is where y is equal to 0. If I put a point, and I'm going to erase all this in a second, so don't bother writing it. If I say, what are the coordinates of this point? You would say, well, I don't know the x-coordinate. Maybe the x-coordinate is -3, but the y-coordinate is 0. So, and it seems like such a simple thing when it's explained to students, but for some reason, students confuse things here. This is the x-axis. So what we're talking about doing is reflecting that arm vertically. And that means it's going to go from quadrant 1 to quadrant 4. And we've already kind of discussed the idea that it's going to have the same reference angle. So I'm just doing this so that I can do a fairly decent job of graphing this, so that it looks symmetrical. And I'm going to have to restart this program. Sometimes this happens, and no matter what I do, I can't get out of it. Give me just 1 minute. Sorry about that. Hopefully that does it. Yep. So, Third time's charm, we'll see. While I'm waiting for this to stop hiccuping, you can go ahead and draw the reflected arm.
I think I lost my.
Oh, you know what? Can I see the one I gave you? This is it. Have you written a lot in here? Okay, so I'm going to give you this one. I found one just on the floor over there, and I thought it was one I dropped, so I put it back on the pile. I'll give you this, and if you want, you can have a new one. There's some writing in there. You have to take a look at it and decide. Okay, sorry about that. Okay, let's take a look now. Okay, hopefully, I'm really hoping here. Okay, we're okay. It's a glitch in the program that happens sometimes. Let me get back to where I can get things going. Okay, so the reason why I did this is I just want to make sure that when I draw this reflected terminal arm, I draw it in, kind of the same angle up as it is down. So we already know that this reference angle is 38 degrees. When you reflect that original terminal arm in either axis, the reference angle stays the same. The question now is, for the new terminal arm, what is the rotation angle? And this is a yesterday question. It's going to be 360 minus 38, which I think is 328. No, 322. 322. Okay. Pretty straightforward, but any questions with B? What if in C we reflect the original terminal arm in the line x equals 0? Well, the line x equals 0 is the y-axis. You can even think of it this way. If I gave you an equation of a graph, an equation of a function, and I said, what is the y-intercept? You're going to change x to 0. Because every place on the y-axis, x is 0. So I can either write the words y-axis or I can write x equals 0. If we draw the original graph or terminal arm, which looks like that, this has a reference angle of the 38 degrees. If I reflect that horizontally, which means across the y-axis, then I'm going to get a terminal arm that is now in this orientation. Again, this is the original, and this is the reflected. You can see that the reference angle is still 38 degrees. But to find the rotation angle, what we're going to have to do is use our knowledge of the fact that it's in quadrant 2 and say it must be 180 minus 38, which I think gives me 142. Is that right? 142? So the rotation angle theta is 142 degrees. I have one more question here before we move on to the more complicated or involved stuff, and it's determine the angle in standard position if we have 135 degrees and it's reflected in the y-axis. And the only there's a couple of things that make this different. One is it's not in quadrant 1 to begin with. 2, I'm not giving you a grid. But I want to impress on you that I don't think most people can answer this question with 100% accuracy all of the time unless they are really good at visualizing the axes and what's happening, or they draw it themselves. So 135 degrees is in quadrant 2. We learned that yesterday. Specifically, the terminal arm will look like that. And I think, am I wrong? Is a reference angle of 45 degrees? 180 minus 135 gives you 45. So this original arm has a reference angle of 45 degrees. So I think just seeing this on paper helps you answer question A. If I reflect it in the y-axis, then it's going to end up in quadrant 1 because it's going to go across the y-axis. If I reflect it in the x-axis, it's going to be in quadrant 3. And if I reflect it in the y-axis and then the x-axis, well, if I reflect it in the y-axis and it goes to quadrant 1, then after I reflect it in the x-axis, it will go into quadrant 4. I reflect it in the y-axis, it's going to end up here. Then I reflect it in the x-axis, it's going to end up in quadrant 4. And really what this boils down to now is you remembering that the reference angle doesn't change. So for A, the problem is if you have a reference angle of 45 degrees in quadrant 1, what's the rotation angle? And the rotation angle would be 45 degrees. Because in quadrant 1, the rotation angle and reference angles are equal. We did this yesterday. If I have a reference angle of 45 degrees in quadrant 3, the rotation angle will be 180 plus the 45, which is 225 degrees. Now listen, if you want to draw that so you can figure out that it's 180 plus 45, that's fine. You can do that too. If I draw a terminal arm in quadrant 3, and the reference angle of that arm is 45 degrees, then the rotation angle will be 180 plus 45. What I'm saying is that little diagram I just put at the bottom of the page, I don't think you need to draw that. How many of you, just curious, how many of you could just sort that out in your head? Okay. And if you can't, then draw it. It's not a big deal. It takes 3-4 seconds to draw it. On the other hand, if we have in quadrant 4 a reference angle of 45 degrees, then we can take 360 degrees minus the 45 degrees. How's my subtraction skills this afternoon? Good. And the reason why that's working is, again, I'm not sure everybody needs to do this, but if I draw a reference angle of 45 degrees in this quadrant, then I have to figure out how I can determine this rotation angle, which is theta. Well, it's going to be 360 minus 45. And that's one of the things that you have to know how to do in this unit. Deal with reflections. But it's not that difficult. Okay, now we're going to move on to the next page. And this is where things get a little bit more complicated or involved. We are going to be working here, everybody, with the traditional definitions of sine, cosine, and tangent, which, by the way, if you were to look at your formula sheet, you're not given these formulas anymore. In grade 10 math, you were given sine of theta equals opposite over hypotenuse. You're not in this course, but you're expected to know that. In grade 10 math on your formula sheet, you were given cosine of theta equals adjacent over hypotenuse. And you were given tangent of theta equals opposite over adjacent. And in the coming days, we're going to talk in detail about what that really means. Even though you learned it already and you should know, there's some things that I want to make sure that you understand. So you're not given these anymore, but you're expected to know them. Okay. Before we get to sine, cosine, and tangent, though, and applying these formulas that are not on your formula sheet, we're going to talk about what are called special angles. In trigonometry, there are certain angles that appear to crop up a lot, either in nature or in math courses, and we call those special angles. And the angles are any angles that are multiples of 30 or 45 degrees. And one of the things you'll notice with a little bit of thought is one multiple of 30 is 60. So 60 is a special angle. One multiple of 30 is 90. One multiple of 45 is also 90, but another multiple of 45 is 135 degrees. So these are special angles. And if you take a look on the right-hand side of the sheet, well, I'm going to ask you to focus up here. What I've got is a circle centered on the coordinate grid, and that green dot, of course, is 0 degrees. No problem there. Remember, we measure angles counterclockwise, and all of these angles that I've highlighted here, I haven't highlighted every one that's on that diagram, but all of the ones I've highlighted are 30 degrees away from each other. I mean, you certainly don't want to do this, but if I were to draw lines from the center to here and the center to here, then I would be cutting that first quadrant into 3 equal parts. And that first quadrant covers 90 degrees. And what I am getting at is what that means is that that must be 30 degrees. And I want you trying to think in terms of pieces of 30. That's 30. This must be 60. This must be 90. I can continue. 90 plus 30 is 120. Plus 30 is 150. Plus 30 is 180. You're going to have to know where these things are eventually without looking at the picture. Plus another 30, 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 plus another 30. This is how I'm getting these numbers. On the other hand, if you look at the screen, these are all separated by 45 degrees. So if we start off at 0 and go counterclockwise to the next point that's highlighted, you get 45. If I go to the next highlighted point, I get 90, but 90 was already covered as a multiple of 30. Go to the next one, I get 135. 90 plus 45. Plus 45 again gives me 180. Plus 45 again gives me 225. Plus 45 again gives me 270, and then 315. And finally, I'm back at 360. You need to know, first of all, the locations of these angles. And it should be something that you can conjure up fairly quickly. You know, where's 315 degrees? You should be able to visualize it. Where's 330? You should be able to visualize it. So, you are expected, and for some reason I'm missing some information here, but if you take a look there, it's okay. I know what it says. Thank you. Though it says you are expected to be able to find the trigonometric ratios of any of these as exact values. So correct me if I'm wrong. Do I have on there cosine of 30 degrees in your notes? Tan of 30? What's the other one? Sine of 45? Cos of 45? Tan of 30 and cos of 45. Is that right? So without using a calculator, you should be able to tell me by the end of this lesson the exact value of the tangent of 30 degrees. And it turns out it's equal to 1 divided by the square root of 3. I know that because I've taken Math 20 and I've learned how to figure that out. And if I were to figure out what the cosine of 45 degrees is, it turns out it's equal to 1 over root 2. And we're just going to play on the calculator for just a minute here. Okay? So if I take my calculator, always making sure that it's in degree mode, and I have to change my setting every time I close my calculator and reopen it, it goes back to radians. I can change that. and I figure out what tangent of 30 degrees is, I get this number. Now, what's interesting here, I think it's interesting, is if I try to convert this to a fraction, I can't. And that tells me that the tangent of 30 degrees is an irrational number. It goes on forever. And we'll review a bit of irrational numbers today, but let's take 1 divided by the square root of 3 and see what we get. We get that same number. I know that the tangent of 30 is 1 over root 3. What about cosine of 45? Well, let's try cosine of 45 on the calculator. Gives me that number. Again, if I try to convert this to a fraction, I'm out of luck because it's not fractionable. That's just the word that I've just made up. It means it's not rational because rational numbers are fractions of integers. This is an irrational number. If I try to take 1 divided by the square root of 2, I calculate what that is, it gives me that number. Before we get into the heart of this lesson now, I want to point something out to you, and we just have to recognize that this is always the case. Can you please figure out what the square root of 3 divided by 3 is equal to on your calculator? Now, when you go square root, you're forced to use brackets, so you have to close the brackets on the 3 and then divide by 3. And in case you've forgotten or you weren't doing it before, what is 1 divided by the square root of 3? So the square root of 3, close brackets, divided by 3 gives me this number. And 1 divided by the square root of 3 gives me this number. It's the same. So what I'm asking of you is to recognize from now on that if you ever see root 3 over 3, it's the same as 1 over root 3. And the same would be true here. Except, of course, there are 2's. And that's always going to be the case. You can try this with any numbers. You can go 1 over root a, and then try root a over a. Doesn't matter what a is. A can be 10 or 5 or 28. It will work. We'll learn why in the next unit. There's a mathematical reason for that. Okay. So how do we do this? How do I know that the tangent of 30 is 1 over root 3? How do I know that the cosine of 45 is 1 over root 2? Or the cosine of 30 is root 3 over 2? I know that. Look. Cosine of 30 degrees, the square root of 3 divided by 2. How do I know this? Well, this is what we're going to learn. The first thing that you need to understand is how to find the missing sides of these triangles. Okay? And this is the warm-up. If we have a 45, 45, 90 degree triangle and I tell you the hypotenuse is 2, the problem is what's the length of each of the other sides? Well, both of those sides are equal in length, aren't they? So why don't we call each of them L? I want to avoid X here and Y. Let's just call each of them L. I can write out a Pythagorean statement based on that, which would be L squared plus L squared equals 2 squared. L squared plus L squared is 2L squared. And 2 squared is 4. L squared plus L squared is 2L squared, just like cat plus cat is 2 cat. I can divide both sides by 2 and get L squared equals 4 over 2, which means L squared equals 2. And that means L is the square root of 2. Okay, so what have we learned? We've learned that for that triangle, if you label the hypotenuse as 2, both of the other sides have lengths of the square root of 2. So this is root 2, and this is root 2. You have to be able to visualize or construct this particular triangle and find those sides. Now, you don't have to use 2 for the hypotenuse, but I'm recommending using 2 because it makes your job easier later on. This one is a little more difficult. I'm going to ask you, without using your calculator or any kind of trigonometry, I'm going to ask, does anybody know the length of this side in this triangle? And some of you might. Jay? It is half of the hypotenuse. It's 1. Do you know why? It just looks like it, doesn't it? Well, I'll tell you what, if we take this triangle, and speaking of reflections, I reflect that triangle across this line. I'll use a different color. I reflect that triangle across that line. And then I get this, don't I? If you look at that whole thing as a single triangle, so we're going to look at this whole thing as one triangle. This is 60 degrees. This is 60 degrees. And this is 60 degrees. You can either figure out that the top angle in that large triangle is 60 by saying all 3 angles have to add up to 180. Or you can say the top angle in that red triangle, the big red triangle, is 60 because it's got 30 and 30 in it. But regardless, this is an equilateral triangle, which means since all 3 angles are equal, all 3 sides are equal, that means that this is 2, and this entire distance must be 2. But since these 2 sides are equal in the 2 triangles, each of them must be half of the 2. So that means it's 1. And you have to be able to go through that process to determine what J has determined. Or you simply have to know that in this triangle, that highlighted side is half of the hypotenuse. Now you know 2 sides of a Pythagorean triangle. You can write out the Pythagorean statement for it. I'm choosing to use L. I'm not sure why I wrote plus L there. You can use L for the length there. It's a different L. So we have 1 squared, which is a short side of the triangle, plus L squared, which is the other short side, equals 2 squared. We end up with 1 plus L squared equals 4. So L squared equals 3. L equals root 3. Okay. Listen, when it comes down to it, I suppose, what I'm saying is you need to know these 2 triangles. If you have a photographic memory, whatever that means, if you're able to memorize things, which I don't think is always the best way to learn in math, I think it's better to understand, and you can memorize those, that's great. I mean, this one's pretty easy to remember, the one on the left. And the one on the right isn't that bad. You just have to know if the hypotenuse is 2, the shortest side is half of that. And then probably by the time you start writing out the Pythagorean statement, you probably go, oh yeah, right, it's root 3. You might remember that. And by 30 you will. By Math 30-1 you will memorize these in a different way though. So why are we doing this? Because I want to know the exact value of sine of 30 degrees without a calculator. And listen, you could use a calculator here. I don't want you to. And figure out the answers to each of these 9 statements with a calculator and a little bit of clever thought. But later on, it will let you down. Okay? I'm telling you, there are shortcuts you might discover, but don't take them, because if you rely on the shortcuts now, you won't understand how to do things later. Does that make sense? You get what I'm saying to you? You may not know why that's the case, but just trust me. I know that this is 1/2. Can somebody, you're going to need to look at those triangles. Can somebody explain why I know the sine of 30 is 1/2? Ashira. Right. So now we're going back to what I told you at the beginning, which is that those trigonometric ratios are not given to you, but you do need to know that the sine of an angle is the opposite side over the hypotenuse. And I understand, based on what you just told me, that your triangle is oriented differently, right? So that's fine. Right? In this triangle, the 30 degrees is at the top. Opposite 30 is 1, and the hypotenuse is 2. So 1/2 gives you the sine of 30 degrees. Now, I'll be the first to admit, let me go back to this. Just quickly, a couple of things. Note that if you look at the 30 degrees here, opposite is 1 and hypotenuse is 2. It doesn't matter which way you do it. I'll be the first to admit that you could certainly do this in this question and go math, enter, enter, because apparently the sine of 30 degrees is a rational number. Okay, let's go on and let's take a look at sine of 60. Well, you look at this triangle and you say that 60 degrees on the screen is at the top, opposite is √3, hypotenuse is 2, opposite over hypotenuse is √3/2. I'm telling you that you need to know the sine of 60 degrees is √3/2. One way or another, you need to know that. What's the sine of 45? Well, we look at the 45-degree angle this time. We've got 2 to pick from. I'm going to pick this one. Opposite is over here. Hypotenuse is here. So it's √2/2. Could I put 1/√2? Yep, they're the same number. It's got nothing to do with the triangle. It just has to do with knowing that fact. Cos of 30, take a look at the triangle that has 30 degrees in it. Cosine is adjacent over hypotenuse. I think adjacent to 30 degrees is √3. Hypotenuse is 2. Cosine of 60, adjacent is 1. Hypotenuse is 2. Some of you will understand that the sine of 30 and the cos of 60 are the same, mainly because 30 degrees and 60 degrees add up to 90. Cosine of 45, when you look at the 45-degree triangle, adjacent is √2, hypotenuse is 2. So you could put √2/2 or 1/√2. Tangent of 30, so you're going to look at the 30-degree triangle. Tangent is opposite over adjacent. Opposite 30 is 1, correct? Adjacent is √3, correct? 1/√3. Or √3/3. What about tangent of 60? Okay, so you're looking at the 60-degree triangle and the 60-degree angle, and you're looking opposite 60. And when you go opposite 60, I believe it's √3, over adjacent, which is 1. Yeah, that's right. Um, well, I'll leave the 1 in there. You don't need to worry about writing 1, but I want to make sure that you see there's an opposite and adjacent there. Tangent of 45 is 1 because it's root 2 over root 2, which is 1. And just use your calculator right now and complete the table for number 3. We're not using this really in this course, but I want you to have it in your notes so when we talk about Math 30 next year, you'll have seen it. Now, next year, I will teach you, assuming I'm teaching this course 30-1 next year, that the sine of 0 is 0 for a reason, the sine of 90 is 1 for a reason, the cosine of 0 is 1, and the cosine of 90 is 0 for a reason. I got them right, I hope. Okay, there's a reason for that. Okay, but it's not really explainable using adjacent and hypotenuse and all that other stuff. So now we're going to apply this. And really, what this boils down to, everybody, is you're solving trigonometry problems using SOHCAHTOA, but you're not using your calculator to calculate values of trig ratios. Let me show you what I mean. We've got a metronome. There's a picture of a metronome in your notes for you, and this arm swings back and forth. The first thing to note is there's a typing mistake in your printout. It says it goes from a start position of 45 degrees to, and then it says to 45 degrees. It should say to 135. So what we're talking about here is the metronome arm goes from 45 degrees, which is this angle, and then it goes to a new position. I'm just using a different color. I don't know, let's use the same color. I guess it's the same arm. So, and then it goes over to here, where this is 135 degrees. And the question is, if the length of that arm is 10, then how far horizontally does the tip of the arm move? What it's asking you to determine is the length of that black line. And this, everybody, is not, except for the fact that it says exact value, it's not a Math 20 problem, it's a Math 10 problem. Because what you have is this triangle where you know this is 45 degrees and you know the hypotenuse is 10. So if you can find this length, which I'm going to call x because it happens to be an x, if you can find that length, then you have to double it to get the answer. Are you with me on that? Okay. So this is a problem that's using SOHCAHTOA. We look at that blue triangle and say the x is across from the 45 degrees. It's opposite to the 45. The 10 is the hypotenuse, so opposite and hypotenuse is related to sine. This is the trigonometric relationship we're going to use to solve this problem. So we put 45 degrees in for theta, sine of 45 degrees equals opposite, which is x, over the hypotenuse, which is 10. And I didn't teach any of you Math 10, okay? I don't know how this is taught to you, but if I were teaching it, the first thing I would do is I would not grab my calculator. I would tell the students, let's cross multiply and write out the statement. The statement is 10 sine 45 equals x times 1, which is x. And again, if you've been taught in grade 10 the fish thing, just stop doing it, please. It's not going to be helpful later on in this course. It would work here, kind of, but it's going to break down later. Okay, so imagine that this is grade 10. Grade 10, what you do is this. Well, you turn your calculator on first. You do this. This is grade 10. And then, of course, you have to double that to get the answer. But this question does not want a decimal answer. It wants an exact answer. Instead of 10? Thank you. So that number should be 7.07. I'll go a little slower here to make sure that I don't make a mistake like that again. Thank you for that, though, that's what a grade 10 student would do, and then they would double it and get an answer of 14.2 or whatever. But we want an exact value. And I don't want to get too deep into rational and irrational numbers, but because the answer has square roots in it, as soon as your calculator evaluates it, it's giving you a decimal approximation. Briefly, forget about this for a second. What's the square root of 2 equal to? Who can tell me what the square root of 2 is equal to? It's a bit of a trick question. Want to give it a shot? You can do it. No. No. Who said that? It's equal to root 2. Because 2 is not a perfect square. The square root of 2 is not irrational. That's right. Sorry, the square root of 2 is not rational. As soon as you go root 2 on your calculator, you get 1.41 something. That's no longer the square root of 2. That's a decimal approximation. And that's why your calculator can't handle putting this into a fractional form. If you tried to put it into a fraction, you can't. So in Math 11, in grade 11, we say, well, I know that sine of 45 is root 2 over 2. Why do I know that? Because, and this is what I just did in my head, because when I construct a 45-degree triangle, and this is 2, these two sides are root 2, so the sine of 45 is opposite over hypotenuse. Goes around in my head in about 5 seconds. That's a bit of a lie. I know the sine of 45 is root 2 over 2 because I've seen that triangle a million times. Okay. So this is equal to x. By the way, since we're multiplying the 10 on the top, the 10 can be thought of as a factor of the top, and I have 2 as a factor of the bottom. The 10 and the 2 can be reduced to 5. So x has a value of exactly 5 root 2. Can you do me a favor and take 5 times the square root of 2 on your calculator? You get this, right? You get 7.07. So there's a way to go from an exact value to a decimal value, but once you're in decimal, you can't go back. The answer to this question then is we need to take the 5 root 2 times 2, which gives you 10 root 2. 5 root 2 means you got root 2 plus root 2 plus root 2 plus root 2 plus root 2. You have 5 of them, and you're doubling that, so you get 10 root 2. Was the 10 in the question in centimeters? Okay, so the answer is this many centimeters. Let's try another one. This is a Math 10 question. I think I pulled it from my old Math 10 lesson. If you want to determine x, would everybody agree that if you knew the length of the hypotenuse in this right triangle that's on the right-hand side, if you knew the length of the hypotenuse, you could use trigonometry to find x. Okay. But that hypotenuse that's in green is part of the triangle on the left. And we know an angle and a side. So in reference to this 45 degrees, this is the adjacent side, and this is the hypotenuse. That means we can use cosine. Cosine of 45 degrees will be the adjacent. Let's call it L. I like the letter L. I would avoid H for hypotenuse because it's only the hypotenuse of the other triangle, not the hypotenuse of the first one. I would just call it L. Over 15, which means when you cross multiply, L is cosine of 45 times 15. And if we were in grade 10, you'd grab your calculator and you start plugging away. We're not. We want exact values. So you need to figure out for me what the cosine of 45 degrees is. And you're looking at the triangle that has the 45-degree angle in it. And you're saying, looking at that triangle, cosine is adjacent over hypotenuse. And correct me if I'm wrong, in that triangle, adjacent to 45 is root 2, and the hypotenuse is 2. So cos of 45 is root 2 over 2. And what's going to happen in a few minutes when you try these on your own is you're going to start, some of you will start putting up your hands. You go, I don't know what to do. And you will be at this stage right here, and you will say, I don't know what to do. And the answer is, you have to figure out the exact value of the trigonometric ratio. So that's that green side. Now let's focus our attention. This is for this triangle. Now let's focus our attention on this triangle, where I have the 60 degrees, x is opposite. That number we just found is the hypotenuse, so I can use sine of the 60 degrees equals opposite over the hypotenuse. I better write this out first. Sine of theta equals opposite over hypotenuse. Okay, what's theta? Theta is 60 degrees. So I have sine of 60 degrees equals the opposite, which is x, over the hypotenuse, which is 15 root 2 over 2. And you're going to have to trust me with something here, which is the proper way to proceed. Okay? How many of you have been taught, well, you've all been taught this, but how many of you remember when you divide by a fraction, you multiply by the reciprocal? It's a quirky little rule. I don't want us doing that. I want us thinking of fractions differently. This is called, bring it up a bit. This fraction that we have right now is called a complex fraction. Why is it considered complex? Because it is a fraction of two things, but in the denominator there's another fraction. You get my drift? It's a fraction of a fraction. I call this thing a mini denominator, and it's a problem. It's got to go. We don't like mini denominators, whether they're in the numerator or denominator. And we can get rid of a mini denominator by multiplying the top of the entire fraction and the bottom of the entire fraction by that denominator we want to get rid of. Dividing by a fraction can be handled as multiplying by the reciprocal, but not all the time, because the fractions can get more complicated. So this is a general rule. What happens is we end up with 2x on the top, and on the bottom what happens is we have 15 root 2. Because these cancel. And this is equal to sine of 60. Well, what is sine of 60? Now you got to go back to those triangles and you have to figure out what sine of 60 is. And I'm thinking it's root 3 over 2. Because when I look at that triangle, now I know it. I'm not looking at a triangle, but I've done this enough that I know it's root 3 over 2. But when you look at that triangle, opposite is root 3, hypotenuse is 2. So you have this equation to solve. Well, let's cross multiply. That means I take the top, which is root 3, multiplied by the bottom, which is 15 root 2, equals the top times the bottom, which will be 4x. So now I can divide both sides by 4 and get x equals 15. Now, you are taught, listen, the further you get in high school math, the more you have to go back to those previous grades for these little tiny things. You were taught in grade 10 that something like root 3 times root 2 is root 6. Okay? You deal a little bit with radicals in root 10. So I can write root 6, and this is over 4. That's x. That's the exact value of x. We have one more quick question to do, and then you're going to try 4 of these types of problems for tomorrow. Okay. What is the exact value of this? I mean, I could train my dog, put little prosthetic mittens on my dog's paws. I could probably train my dog to use a calculator. That's an exaggeration. She would never be able to figure it out. But the point is, we're not here to plug stuff into our calculator. What is 1 minus cos 30 minus sine 45? Well, cosine of 30 is root 3 over 2, isn't it? Is there anybody in the room who's slowly starting to know these without looking all the time? A few. Okay. Minus sine of 45. Well, that's root 2 over 2. Looking at the triangle. I would prefer to put these together with a common denominator. And that would mean I can multiply the top and the bottom of that first number of 1 by 2 and get 2 over 2 minus root 3 over 2 minus root 2 over 2. That's the answer. And, you don't have to like it, but it's a reality. This could be a numerical response question where I say that 1 minus cos 30 minus sine 45 equals a minus root b minus root c over d. What are the values of a, b, c, and d? Well, a is 2, b is 3, c is 2, d is 2. Listen, all you're doing for these 4 problems that are on the next page